In the last video, we saw how to model the reverse recovery characteristics using PLECS. Now for that example, we took a diode from Infineon, which was the 6001N. And if you remember, the condition for producing that recovery effect was listed as shown here. So under this certain criteria, we were able to simulate the characteristic curves. Now in the practice, it might not be the scenario depending on different applications. For example, there we had to calculate the stray inductance depending on these criteria specified here. But maybe in reality we have different kind of stray inductance. Maybe we have a different load characteristic. Or maybe we have a reverse voltage different than 1000 volt as specified here. Now to consider this type of scenario, let's modify the previous model and adjust it according to the new assumed model parameters rather than the specified test conditions here by Infineon. So go to the model first. I will save it under different name. So it's diode reverse recovery. Let's call it a snubber. Now why do I call it a snubber? Because as I mentioned, under these conditions we had these two values of these RC snubbers, one 6 microfarads for capacitance and 4.7 ohm for the resistor. Now if we change the test conditions, now these values have to be calculated new. So this is the target for this tutorial today. I will also save the script under different name. Let's call it reverse recovery, then snubber and initialization. Now for the sake of this tutorial, let's take the DC current 2 kiloamperes instead of 1. And let's also take the reverse voltage to be 2 kilovolts instead of 1. Now we also need to check if we calculate the snubber parameters new, if it is still possible to keep the peak voltage within the specified range, 5 kilovolt as in the datasheet. If it is not, we need to recalculate for different levels. I will define them later, RS and RC, depending on what we have. So let's assume we have, so these are fixed IDC. I take it from the conducting current before switching off process turrets. Didt we need to calculate. It was given for the test conditions, but for our case, as I said, if the test conditions change, then the Didt also change. So based on these two assumptions, that we have the current and the blocking voltage, we can calculate the Didt, which is VR divided by Didt is VR divided by LS. So maybe for the assumed circuit we should know the inductance in the path, and that is what we write here, LS. Let's take it 0.4 millihenries. This is the stray inductance. So from these three values we can calculate Didt. Now this is an important point. If we specify IDC and VR and L, if these three variables are fixed, then the Didt is going to be fixed. And we need to find that Didt and go to the datasheet to find or to read these two parameters. Let's run it first to find out the Didt. Or we can also calculate it if we just run this here, evaluate selection, we should be able to get DIDT. So DIR DT. This is okay. 5 ampere per microseconds. If I read 1, 2, 3, 4, 5, 6. So it is 5 amperes per microsecond, the DIDT. If we look carefully into the data sheet of the diode, there should be a DIDT dependent curve for the recovered charge and also for the peak reverse current. Now let's read for 5 ampere per microseconds the values of QR and IR. 5 is just 1, 2, 3, 4, 5, 6, 2, so it's somewhere here. In the middle it's 5. And then I will take VR max is specified to be 1000 volts. It's max. But for the sake of the tutorial, we said let's to be 2 kilovolts. So if we read the values here, it's somewhere 10.5 milliampere seconds, I would say. This value is 10.5. So Q's 10.5. And let's do the same for a reverse current. So 5 is here. If we go up somewhere as 200, and this is 50, no, 200 to 300 is 250. 1, 2, 3, 4, 5. So 1, 2. This is 3. 1, 2, 3, 4, 5. So if I read 5 amperes per microseconds here and go up, it meets here. So each division is 20 amperes. 5 is 100. Yes, then we are here. So 240 amperes, I would say, approximately. 240. Once we have these values, we can calculate this Snubber capacitor as LS times IRRM divided by VR, and that is squared. And for RS it is 1.3 times simply VR divided by IRRM. So these are the values. Now, of course, we considered extreme high values, I think, for these diodes, but let's check how they look like. It is not updating. Diode BRR Snubber. Now it should update. So let's see our current. Let's take it to 1000 amperes flowing before it stops. Now DIDT, as I said, should be 5 amperes per microsecond. Let's check if the rate is correct. That's why we need a delta, and I will specify 1 micro here. And if we take these locked cursors here, we should be able to see 5 amperes per microsecond. For in this space of fall, a time space where the current is falling, it is 5 amperes per microsecond. Conducting current is 2 kiloamperes, and if we take the reverse peak current to check. This is around, we need to take the minimum in this region. It's 240 as we read from the datasheet. That means, and if the operating condition is changed this way, we should get 240 reverse current. Let's simulate it a little bit longer. Let's make it 6. So you see our reverse voltage in that case is 2 kilovolts. When the reverse characteristics is gone, then we have 2 kilovolts. Now this peak voltage is around 3.6 kilovolts. That means we still have some reserve until we reach 5 kilovolts as specified in the datasheet. Under these operating conditions, it is still safe to run the converter with this diode and under these conditions. That means if we choose the value of the snubbers as calculated here, we can damp actually the peak here quite good. Let's check what the values of RS and CS are. Should go RS, it's 10 ohms, and CS is 5.76 microfarads. So these values are sufficient to optimally damp that peak voltages here. If what happens without the snubber circuit is catastrophe, if we don't have the snubber circuit for this case, and if the conditions of the operation is quite worse, then the diode can go damaged anytime. So these snubbers are there to protect them. Now these two formula, I think they are present in Power Electronics book by Ned Mohan, if I'm not mistaken. And let's check if we have, okay, here we see something different. Okay, I think this is clear because the time when the current reaches 0 point is different. This is remaining from the previous simulation. Let's check it when the current reaches the 0 level. It is around, I see it's around 1.4 milliseconds. Yes. Now if we set the value of stepping as to 1.4 milliseconds, then we should be fine. And yes, here we have the correct values. Let's check it if we can read it better. It's 10.5 milliampere seconds. So it's quite good. This is how we can calculate the snubber parameters for a single diode depending on different test conditions as specified in the datasheet. I can also write a sweep parameters, for example, if we have different inductances, how would be the characteristic curves for that. And for that we will make some later videos as well. But that's all for today. Thank you.